So the 2012 FRQ problem number 6 covers material that is the most recent, so it should be the freshest in our minds. I'll just insert an awkward pause there. But the first thing we need to do here is recognize that we're given a Maclaurin series for some function g, and the first thing that they ask us to do is to use the ratio test to determine the interval of convergence, which is a good thing because that's exactly the test that we should be using. So just to recap the ratio test, we are going to find the limit of a sub n plus 1 over a sub n. So let's find the limit as n approaches infinity of the absolute value. And since I'm taking the absolute value, that means I really don't need to look at this negative 1 to the n power term. I really just need to look at this portion of our general term. So we can just go ahead and do x to the, now if I'm plugging in n plus 1 in for every n, this should then give me x to the 2n plus 3. And again, if I'm replacing all my n's with an n plus 1 and distribute, that should give us 2n plus 5. That's our a sub n plus 1 term. Divide that by a sub n, which just means multiply by the reciprocal. So 2n plus 3 over x to the 2n plus 1. Okay. Now, from here, as I'm taking the limit as n approaches infinity, the only thing that really matters are the terms with an n in it. And before I continue, I should probably clean this up a little bit. I've got an x to the 2n plus 3 over x to the 2n plus 1. And if you want to see how we could just simplify that a little bit, we should just get x to the second power left over. So this should be x squared. Now, some people like to leave that inside the absolute value. Sometimes some people like to take that outside. It doesn't really matter, honestly, because again, if we're taking the limit as n approaches infinity, the only thing that is affected by us taking the limit are the terms with n in them. So we really just need to look at this for now. And again, if you want to leave that x squared on the inside, that is totally fine. The limit as n approaches infinity of this term would just be equal to 1 times x squared, and that just gives us x squared. Now, an interval of convergence occurs when the result of our doing the ratio test is when it's less than 1. So ask yourself, when is x squared less than 1? Well, x squared is less than 1 when x is less than 1 and it's greater than negative 1. And if you're having a hard time visualizing why that is the case, just think about the graph of the parabola x squared and see for what values of x would that parabola be less than 1. Now, the next thing we need to do for our interval of convergence is to actually test the endpoints. So let's just switch colors here so it's clear that we're working on different endpoints. So let x be equal to negative 1. And when x is equal to negative 1, and that means we're looking at the summation of negative 1 to the n times x to the, well, that's negative, plug in, negative 1, not x, negative 1 to the 2n plus 1, all of that over 2n plus 3. And however you want to think about this right now, you should be able to simplify that numerator until it just resembles something like this. Well, we know that negative 1 to the 2n is always just going to be positive 1. So we're really, in the second term in the numerator, we're really just looking at negative 1 to the 1 power, which is always negative 1. So that would just be negative 1 to the n plus 1 all over 2n plus 3. And let me make that more obvious that it's an exponent. And hopefully it jumps out to you what tests we should be using by the alternating series test. All right, we want to show the two conditions. All right, the first condition is we know that the limit as n approaches infinity of 1 over 2n plus 3 is equal to 0. And the second condition is that a sub n decreases in absolute value. right? A sub n is actually decreasing in absolute value. So we can say A sub n decreases in absolute value. So since we know that it's met the two conditions for AST, we can say that it converges by AST. So we can say that for our interval of convergence, we know that so far it's definitely converging at its endpoint -1. Now let's check the other endpoint. When x is equal to +1, so let's look at that when x is equal to +1. So same sort of deal. That should plug into -1 to the n. And let's just make sure I remember what that original general term looked like. We have +1 to the 2n plus 1. Let's just write that. All over 2n plus 3. And that should clean up quite nicely to just -1 to the n over 2n plus 3. And again, same test. It's going to be pretty obvious to us that it's going to converge by the alternating series test for the same reasons that we said above. So again, the limit as n approaches infinity of 1 over 2n plus 3 is equal to 0. And again, 1 over 2n plus 3 is greater than 1 over 2n plus 5. So a sub n is going to decrease in absolute value. Okay, so we see that it does converge by AST, so it's also going to converge at this endpoint. So we can say that our interval of convergence are all values from -1 to +1. Okay, so you might want to write a concluding statement or just box this, and we have that obvious there, clearly there, that it's converging for those values. Okay, all right, so moving on to the next part. So we read through this problem and we're seeing that we are being asked to show that the approximation that's given to us, 17 over 120, it differs from the actual value of g of 1/2 by less than 1 over 200. And the big thing here, as a bit of a relief to us, is that we're told that it's an alternating series whose terms decrease in absolute value to 0, which tells us that we can use the alternating series error here. And to again review what the alternating series error says, it says our alternating series is always going to be less than the absolute value of the first unused term. It's the absolute value of the first unused term. So we're actually going to need to find the first unused term here. So let me actually bring this down just so that we can have the series here in front of us. Let me go ahead and grab that again. All right, so now that we have this here, we're told that we're using the first two non-zero terms. So that means our first unused term would then be this term right over here. Okay, that is our first term after the first two non-zero terms. So if we are trying to approximate g of 1/2, all we're really going to do is say 1/2 raised to the 5th power, we're plugging in 1/2, all over 7. Well, that's going to be 1/7 times 1/2 to the 5th. So 2 to the 5th power is 32 times 7. I believe that's 224, if I'm not mistaken. So that should be 1 over 224. And that is definitely less than 1 over 200. Okay, so what we've just done is we've just shown that our alternating series error which is less than the first unused term. It's going to be smaller than this value that we've just found here. And this already is less than 1 over 200. So the approximation for g of 1/2 of 17 over 20, That is a really, really good approximation. We know that the error, or how much this approximation is off by, is going to be even smaller than 1 over 200. It's going to be smaller than 1 over 224, which is already a pretty good value. Now, the final part here is to simply just write the first three non-zero terms and the general term of this Maclaurin series for g prime of x. So we're going to start off with the easy part, which is just to find the first three non-zero terms. Well, g prime of x, and we're just going to do term by term differentiation. We're just going to find the derivative of each term here. So the derivative of x over 3 is just going to be the coefficient, 1/3. The derivative of x cubed over 5 is going to be 3x squared over 5. The derivative of x to the 5th over 7 is 5x to the 4th over 7. And this is an alternating series, so we're going to put that minus sign there. And it only asks for the first three non-zero terms, so I'm just going to do this dot, dot, dot. Say, hey, there's an infinite number of terms between that and what we're going to write for our general term. So now we're finding the derivative of our general term, which is this stuff over here. So we're going to find the derivative of that. Now, I know that looks pretty gnarly, but remember, when we're doing the power rule, the only thing that's impacted by the power rule are the terms with x in it. So that -1 to the n and that 2n plus 3, those are just constants. So let's just go ahead and write those so that we don't get too swept up by them. These are just constants, and you know that those constants aren't going to be affected by us applying the power rule. So when we're just doing the derivative of x to the 2n plus 1, that's going to be 2n plus 1 times x to the, and we are going to reduce that power by 1, so 2n. And we are going to put those ellipses here to show that this series is going to go on forever. And that's pretty much it. And if you want to get a little bit nicer, you can go ahead and just put all of that in the numerator if you want to. But that's that. There is the series for the Maclaurin series for g prime of x.